Okay, and that's going to be, I believe, 90 newtons. Down. I think that is 2 sig figs on that. It should be. That should be 2 sig figs on that, guys. I'm okay with that, but should put a little decimal right there, okay? All right. Oh, it's 120. No, it is 1 sig fig because of the way the math works. This works out on this. This is going to be basically 120 with 2 sig figs. It is 90 with that. But if you, I don't care, guys. If you write that way, I don't care. I mean, I got bigger fish to fry. This is 90 newtons. And it is up, and it's not down. Yes, you're going down, but your applied force is up, correct? Because of what I told you. All right, that has number 5 done. Now number 4, or number 6. I'm sorry. Okay, a box rests on a desk. What is the normal force on the desk from? What is the normal force on the box from the desk? Let's say, I don't want to change the camera because I want to get out of here. Let's say my hand is the desk, okay? It rests on the desk. I want to know the normal force of the desk on the book. Well, if my hand's the desk, my hand puts a force upward on the book. So let's say the desk, my hand puts a force upward because gravity's pulling it down. It ain't dropping anymore. I must be pushing back up on the book. We call that the normal force, once again. The normal force, guys, is always perpendicular to and out of the surface. So if I'm pushing this way on a surface, the surface pushes back that way. If I push this way into the wall pushes back that way. If I push on the ceiling ceiling pushes back that way. Okay, perpendicular to and out of the surface. That's the normal force, all right? Make sure you understand the normal force. It's just surfaces push back when you push on them. And basically, the normal force is a reactionary force. If the wall didn't push on my hand until my hand pushes on the wall, it reacts to it. The normal force, the floor pushes up on my feet, but it doesn't do that until I push down on it. Makes sense? It's a reactionary force. All right, good. Let's go. So here I have a box lying on the desk. I want to know what the normal force is on that box. All right, let's do that. If I can find my pencil. There it is. All right, here we go. Let's do the free body diagram. FA is up. Oh, no. The normal force is up. I'm sorry. Normal force. There is no applied force here. And mg is down. All right, that's it. That's your free body. No, sheesh. Sorry, guys. No, I'm tired, folks. Okay. Free body diagram. Normal force is up. The desk is pushing up. mg is pulling down, right? That's your free body diagram. Let's do the givens and unknowns. As I recall, the mass is 5 kilograms. Okay. We'll look for the normal force. What's your acceleration on the y-axis? It is 0 because you're not going anywhere, right? So on the y-axis, your acceleration is 0 because it's not moving. It's just sitting there. Okay, I'm looking for the normal force. It is a y force, therefore summation of y forces. You will find it in the y force. Because the acceleration is 0 on the y-axis, 0 times m is 0, so the right side is 0. That has the right side taken care of. Now the left side, sum up the y forces, n minus mg. N is up, mg is down, add it, subtract it. Solve for the normal force. And that's pretty easy to do, isn't it? So it's going to be the mass, which is going to be 5.0 times 9.8. That is 49. 49 newtons up. That is your normal force. Okie dokie. A little better. Now let's look at number 6. Well, that was number 6. Okay, number 5 and number 7. Now, 7 and 8 are similar problems. Let's discuss the theory on these things, okay? Let's say I have a rocket. I need a rocket. Here we go. This is my rocket. Okay. Now, I'm going to, let's see, let me see if this shows up. This is the launch pad right here, okay? I want to make sure it's on the camera. Oh, sheesh. Just a sec. Make sure everything's there. Can you see? No, you can't. Bummer. I'm going to come down just a little bit, guys. That ought to do. That's pretty good. Those are those books that are right at the bottom. Here's the books. Let's say that's the launch pad, okay? This is the rocket. Now, here's the deal then. As that thing sits there, the known force is that, and mg is down, right? Okay. Now, let's say I give you so much applied force in this thing. It's the thrust of the rocket. The rocket pushing it up. It's thrust, okay? Well, it's constant. Now, I'll give you a certain amount of applied force and pushing up on the rocket, and I'm also going to give you the mass of the rocket. First thing you want to do is the rocket going to take off? All right. Now, how do we understand that? Okay. Well, I know that the applied force is F of A, right? And mg is the force down. And so let's say on this one problem I do here, the rocket is 15,000 kilograms in mass. The applied force is 110,000 newtons, correct? Will it take off? Well, I know this. That's your m. M times g gives you the gravity down, doesn't it? I'm going to ballpark this. I'm going to say g is 10. It's actually 9.8. It's close. So g is 10. What's 10 times 15,000? Because that's m times g, right? That's 150,000. That's the way to gravity down. What's the applied force up? 110,000. That 150,000 is bigger than 110,000. Is it going to take off? No, because gravity is greater than the applied force. Now, if it doesn't take off, it cannot have any acceleration, can it? Because it's just going to sit there. But it does. But the free body diagram of that is different than if it does take off. Here's the free body diagram if it does not take off. Okay. Here you go. Now the applied force is up. Fa is up, right? Mg is down. You with me? Now, if it's going to sit there, there's also a normal force helping hold it up. Now, let me tell you what's going on here because of the normal force, okay? Let's keep this really simple. Let's say I have a Coke bottle. And let's say its weight is 10 newtons down. That's a Coke bottle, okay? And let's say you pull it 4 newtons. It's not going to leave the surface, is it? But I do know this. If that thing's not moving, the force is up. All the force up must equal the force is down because the net force is 0. It's not going to go anywhere. It's not going to accelerate anywhere, correct? So therefore, the known force in this case would be 6 newtons up because 6 and 4 makes 10. That makes sense? That is essentially what's going on here. If you're not taking off and there is a known force, then the known force is going to be up as well, right? Because this force plus this force must equal that force because you're not going anywhere. All right? These forces up must equal that force down if you're not going anywhere. Then that force must be 0. All right? Okay, now, that's how we're going to set up this problem, okay? If it's not taking off, that's your free body diagram. All right? And in this problem here, it doesn't take off. So we know that's the free body diagram. And furthermore, what's the acceleration? 0 meters per second squared. All righty? Let's get rid of this. So that's your free body diagram, that's your acceleration on the y-axis. Now let's do the problem, okay? So it does take off, it has a normal force because it's resting on the surface. Let's find the normal force. Okay, here we go. Let me write all my gills real quick down here. Okay, let me put it on the overhead now. Here's the setup, guys. Now, free body, there's your gills, 15,000 kilograms for the mass. Applied force is that much up, 110,000 up. Let's find the normal force. The course of the free body diagram looks like this. Are we good? Applied force is up, normal force is up, mg is down. Now, I want to find the normal force, don't I? It is a y force, therefore summation y forces. These y's are just subscripts, correct? Okay. Now, what's acceleration on this axis? What's a of y? It's not moving, therefore 0. 0 times anything equals 0. The whole right side is 0. What's this side here? Sum up the y forces. You have 3 of them, right? These are up, so you add them. These are up, so you add them. mg is down, so you subtract it. And solve for your normal force. $40,000 newtons up. Now you're going to get 37,000 newtons on this thing right here, okay? But I'm using the right sig fig, so it's going to be 40,000 newtons. If you write 37,000 newtons, I don't care. That's fine. It's close enough for me. All right. That one is that one, okay? Now let's look at the next scenario. Let's say. Now let's see. Oh, let's look at this one. All right, here we go. Erase this. I'll leave that there. Now, there's the problem, okay? Same rocket, 15,000 kilograms, is on the launch pad trying to take off. If the thrust produced by the rocket is 340,000 newtons, will the rocket take off? And if it does, what's the acceleration? If it doesn't take off, it's got a normal force then, right? I want you to find the normal force if it doesn't take off. Well, let's see if it takes off first. That's m times g. That's your m times g. It's going to get you around 150,000 newtons, correct? That's your applied force. 340,000 newtons up, 150,000 newtons down. It's going to take off. That force is bigger than that force, all right? So if that's the case, what's your free body diagram look like for this situation? So this was the other one, right? Fe up, n up, mg down. But you're taking off. It's not on the surface, right? So you cannot have a normal force. And the surface can't push on the thing if it's not on the surface. So you don't have this force for this one, okay? And if you don't have a normal force, remember, the applied force is not bigger than gravity. Therefore, when you have an imbalance of forces, you have acceleration. This force is greater than that force, you're going to accelerate upward, aren't you? We're looking for the acceleration upward. All right? So that's not 0 anymore. That's your free body diagram. Let's solve for the problem. Here we go. Okay. Here's your free body diagram. I'm going to do this. We don't want to write on the edge. Fa is up. M times G is down. Okay, your applied force, 340,000 newtons. And let's see, we'll look for the acceleration, aren't we? On the y-axis. And let's see, what is the mass? 15,000 kilograms. All right, there's the gives and the unknown free body diagram. Now, because they're y force and y motion, summation of y forces. That'll drive me nuts. Look it up. Now, we're looking for the acceleration, correct? So this side does not go away this time. This side says sum of the y forces. You got 1 up, 1 force down, add it, subtract it, correct? FA minus mg equals m times a of y. I set your acceleration. So divide both sides by m. This m comes over. I'm going to flip it. And then this is going to be over here, right? So 340. Plug all that in, you get, I'm not going to plug it, I'm just going to look at the answer. You get 13 meters per second squared out. There you go. Easy enough. All right, good. Now next one. And it's going to be this, number 9. Interesting. This is finally a y problem. That's interesting. Let me check something real quick. Yeah. I want to change things a little bit because that's not the one. That's not the right worksheet. I'm skipping some problems there. Let's find the right one. Give me a sec. See. That's, let me check. Well, we did one. That's the right worksheet. I did one of those. Let's see. Was somewhere there? Bummer. Well, it's not going to hurt anything. We did a problem that we didn't have to do. It's no big deal. Let's keep going, okay? I have the wrong worksheet. I mean, there are basically some very almost identical problems. I just did one I didn't have to do. That's 6 and 7 there, or 7 and 8 on the that I just did, okay? All right. Yeah. I just skipped one there.